In our previous videos on curve sketching, we were using the first derivative test to find local maximums and minimums and to find where our function was increasing and decreasing. We're going to continue our discussion of curve sketching, but we're now going to add a new element into the graphs, and this is going to help us to get a much more accurate graph than what we previously were able to get. So let's look at the equation y equals x to the 2/3 and use what we've already been using to get the graph. So let's start by taking a derivative. So if I take the derivative, I'm going to get y prime is equal to 2/3 x to the negative 1/3, which would be 2 over 3 cube root of x. So if I want to get critical points, remember that we want to know what makes our derivative be either 0 or undefined. Well, because this is a rational function, we'd want to know what makes the top 0 or the denominator 0 or the numerator 0. Well, in this case, nothing's going to make your numerator 0 because it's 2. But the denominator would be 0 at x equals 0. So that's going to be our only critical point. So if we draw or make our sign chart with the critical point of 0, so let's pick a number less than 0, like negative 1. And substitute that into our derivative. Well, our numerator is always 2, so it's positive. On the bottom, we're doing the cube root of x and then multiplying it by 3. But if I use negative 1, the cube root of negative 1 is negative 1, times 3 would be negative. So I have a positive numerator divided by a negative denominator, so that's negative. And then if I pick a number bigger than 0, let's say 1, put that into my derivative, I'm going to get a positive again on the top. The cube root of 1 is positive, times 3 is positive, and so that's positive. So looking at my function decreases, and then it increases. Well, it decreases from negative infinity to 0, and it increases from 0 to infinity. But if we look at that graphically, that could look like this. Decrease to 0, increase after 0. Well, we know our graph can't look like that because that's the graph of a parabola, and our graph was y equals x to the 2/3. Here is a good example of where you need to be able to find concavity, because what happens is this graph actually looks like this. We are decreasing, but instead of opening up, this graph starts opening down and decreasing, and then it ends opening down and it's increasing. So this is the graph of y equals x to the 2/3, but it has the exact same sign chart as y equals x squared. So that's an example of why you'd want to know how to find concavity. So let's take a moment to look at what we mean by concavity, concave up and concave down, when we're looking at something graphically. So let's look at concave up first. So let's say that our graph resembled that. Well, in that case, we would say that that graph is concave up and it's increasing. If our graph was on the other side, it would be concave up and it would be decreasing. Now, even though when I drew it, it looked like I was drawing it, so it was increasing, we're moving from left to right. And as you move from left to right, that graph is decreasing. Now let's look at concave down. Concave down, we might have a graph that looks something like that, where the graph is opening or bending downward. So in that case, we would say that that part of the graph is concave down, but it's increasing because from left to right, the graph is going up. And the last thing is we have something that looks like that. And in that case, we would say that our graph was concave down again, because it's bending downward, and it's decreasing. So one way that you can remember this is that concave up is like a cup, concave down is like a frown. So if you're concave up, you open up like a cup. If you're concave down, you open down like a frown. So let's take a moment and look at some definitions and some theorems that are going to be important throughout the rest of this lesson. So we're going to first start with some definitions. We say that if a graph is differentiable, meaning the derivative exists, then it is concave up on some interval I if the derivative is increasing. It's said to be concave down on the interval I if the derivative is decreasing. So let's look at that for just a minute. If we were looking at the graph here on something that is concave up, so we'll just kind of sketch a graph that's concave up. Notice that what's happening here, if you were to look at the derivative, which would be the slope of the tangent line, on this side of the graph, the derivatives are all negative, but notice that they are approaching zero, so they're actually getting bigger. Then once we get over here, the derivatives are positive, but the graph is getting steeper, so they're increasing. So in that whole interval, that graph's derivatives would be going from negative numbers to positive numbers, and they would be increasing. If we were concave down, then our graph looked like this. And notice what happens here. If we look at our tangent lines, over here we have positive slopes that are steep, but now they're starting to approach zero, and then our slopes become negative, and they're getting steeper, so they are decreasing. So those values are getting more negative. So in that case, our slopes or our derivative would be decreasing. Now we're going to look at the second derivative test for concavity. So this is going to allow us to work these problems out algebraically. So if y is a twice differentiable function on some interval I, so we can take two derivatives and they exist, then if the second derivative is greater than 0 on the interval, then we say the graph is concave up. And if the second derivative is less than 0, or it's negative, then the graph of f is said to be concave down. And that's really what we're going to be using as we are looking at finding concavity for our functions, is we're going to be looking at the second derivative and looking at its sign. So you might see that we're going to be using some second derivative sign charts, very similar to what we did with first derivative. One last thing we want to look at is another definition, and this is a definition for a point of inflection. We say that a point C, f of C, where the graph of a function has a tangent line, so that's important, and where the concavity changes is called a point of inflection. So as long as your derivative exists and you have a concavity that changes either from positive to negative or negative to positive, then the point where that occurs is called the point of inflection. So looking at that graphically, let's look at a real easy function that we're very familiar with. Let's say we looked at the graph of y equals x cubed. So the graph of y equals x cubed looks like that. And if you notice what's happening here, you actually have two different concavities going on. The first part of this graph here is concave down because it's opening down. The second part of the graph at the top is concave up because it opens up. And what happens is at this point, you have a point where the concavity has changed, so that point becomes our point of inflection.